Hello everyone, I'm Jashwan, team lead of Team Vasistaa from SRK Engineering College, Bhimavaram, and our problem statement is smart, Sambarmati, riverfront and urban water bodies. Our project is Smart Drone Enabled Water Quality Surveillance System designed for real-time high precision monitoring of the Ganga River and its tributaries. It integrates a sophisticated payload onto a multi-rotor UAV platform and high-performance onboard companion computer.
Hello everyone, I'm Himabindu. Coming to key modules, the sampling module is the lightweight corrosion resistant unit that automatically collects contamination free water samples from the specific depths. The smart sensing areas used to integrated sensor for dissolved oxygen pH and temperature to provide real time geotagged water quality data. Finally, the real-time telemetry module uses 5G connectivity to instantly transmit sensor data and flight logs to centralized web page for live monitoring and quick decision making. This slide the vision and navigation module. It combines the thermal and normal cameras processed by the Jetson Nano. The system detects water presence, identifies floating garbage and pollution, and uses time of flighting sensor for centimeter level altitude precision. These ensures the UAV captures accurate and clean water samples during monitoring.
Coming to the design and technical core, the drone hardware and airframe. The airframe utilizes carbon fiber reinforced polymer sheets and tubes, which are up to 3 times stiffer and half the weight of the traditional materials like aluminum and steel, maximizing our endurance and payload capacity. We use a quadcopter with Hobby Wing X6 Plus motors providing a total thrust of 47.6 kg force. This gives us a mandatory 2:1 thrust to weight ratio, providing a safety buffer against unexpected wind gusts and allowing for future hardware expansion, ensuring the drone can always fly safely even with payload additions. A arm holder which holds tubes which are connected to the motors. Next, motors and propeller. Motors which gives a thrust of 11.9 kg. Next, water sample collecting tank which collects more than 1 liter. Next, a battery. As per the dimensions which are available in the market, I designed a battery. Next, carbon tubes which are OD of 30 mm and NRI of 27 mm. Next, coming to the battery compartment, which allows two batteries which can store inside the compartment. Next, servo motor, which are used in arms of pH sensor holder. Coming to the arm mechanism uses servos for movement, which allows the sensor to dip into the river. Coming to the final prototype of a drone, here is it is. Here is the battery compartment which can store up to 2 batteries and the water sample collecting tank which can collect more than 1 liter. Next, the pH sensor, the pH and OD sensor which collects sensor data from the river using the arm which can move by the help of servos. Next, coming to the overall dimensions of the drone, we can see the total length of the drone is 1890.076 mm and the base plate is 300 mm length and 200 mm width. Coming to the payload, the drone can deliver a maximum thrust of 47.6 kg force. As to calculate the payload, we need to calculate the maximum takeoff weight. As per the maximum takeoff weight, the thrust to weight ratio, we need to divide it by 2. We're getting at around 23.8 kilogram force thrust. As that, we need to subtract it with the components on the drone. I will be getting around a 14.312 kilograms of weight. Subtracting the components of weight in the drone, we are getting around a maximum payload of 9.48 kgs. This is the payload of our drone. Here is the components we are using in the drone. Here motor, batteries, carbon pipes and arm holders and carbon sheets and main component NVIDIA Jetson Orion and LiDAR GPS and propellers and tank. Coming to the static analysis, we done analysis on carbon tubes, which will provide a force of 116.73 newtons, which a individual motor can produce a thrust of 116.73 newtons. As per the datasheet, we used this force on the carbon tube. As per the results, we get a maximum safety factor of 5.669. Coming to the technical approach, we use middleware as ROS2 for its performance and flexibility. The ROS2 can programmed by using C++ and Python. For sensors we use C++ and for computer vision we use Python. Coming to the microprocessor, we use Jetson Nano Orient for its processing and edge computing. It can easily runs Python based computer vision and GPU tasks. Coming to the flight controller, we use Pixel Cube Orange for its high reliability and stability and precise GPS navigation on autonomous missions. Coming to the sensors and ranging interface, we use a LiDAR and time of flight sensor for their precise and accurate data. Coming to the communication module, we use 5G module provides high bandwidth and low latency wireless connection, which ensures high speed data communication between ground station and the drone. Coming to the automated sampling and environmental sensors, we use pH, DO and turbidity sensor. Coming to the web server, we use Node.js for the central dashboard, which shows the geotagged and sensor data of the samples.
Hello everyone, I'm Rohit Kumar. Coming to this system methodology and data flow, here we use navigation safety, sampling validation, preliminary visualization. Here we use QGround controller, PX4 flight controller, radar systems, and TOF sensors. These three are interlinked to ROS framework. Here we can see this all data transfer in the real-time dashboard. Here we use speed sensors like on-time computer vision, onboard camera computer vision to visual assignment to the auto seal sampling bottle. Coming to this three stages, key stakeholder and alignment and technology integration and autonomous execution, and also the third stage is to data delivery and enforcement. Coming to this feasibility and viability, here we use some analysis on feasibility like proven technologies, platform maturity and robust software, reliable sensors, strong communications, etc. This is the potential challenges and risks here. So like payload constraints, environmental risks, sensors limitations, connectivity issues. These are the challenges and risks. These are the strategies for overcoming challenges like lightweight design, durability, sensor reliability. Coming to the impact and benefits, this is the primary impact of systems like real-time data-driven enforcement for NMCG and state pollution control boards. This is the public benefits like boosts transparency and public trust, and this is the improved safety like UAVs reduce need for human presence and dangerous sampling locations. These are the benefits of solution like environmental and social benefits, high data integrity, improved safety, supports legal actions, etc. These are the economic and operational benefits like cost effective and fast, efficient resource allocation, and scalable nationwide. These are the research and reference links. Thank you.